So the first application of Green's theorem that we're going to see is going to be in the direction of calculating a double integral using a line integral. So let's recall Green's theorem. Green's theorem, after we clarified all the little details, tells us that if you take a vector-valued function, a field, then integrating the line integral of the field equals integrating the double integral over the domain which the line is its boundary of some derivative-like expression relating to the field. Okay? And we'll see later on why is it specifically this thing and not something else. Well, it's not a mystery. It's something that will be revealed, but it will be in a bit later. So this is the formula we want to use, and the example that we're going to see, let's find the area of an ellipse. Area of an ellipse. Remember that the length of an ellipse, and ellipse is used, the same word is used for the inside and for the boundary, right? It's not a separate word. So the length of the curve that is the boundary of the ellipse is something we don't know how to calculate. We discussed that. There's no closed formula. But the area of an ellipse we do know, and let's find it. So how am I going to do that? It's going to be a bit of magic, but after the magic, you'll see where it came from. So let's consider the field fxy, which is the following field, minus y in the I direction, plus x in the j direction. Do you agree that this is a legitimate field? This is its p component. This is p of x and y. And this is its q component, q of x and y. Do you agree? Okay. Do you agree that this field is clearly in C1, because the partial derivatives of both the function minus y and the function x are continuous, both with respect to x and with respect to y? Do you agree? Okay. So let's write what they are. In order to use Green's theorem, I need the derivative of q with respect to x and the derivative of p with respect to y. So what is qx, the derivative of q with respect to x? It's just 1. And what is the derivative of p with respect to y? Minus 1. Do you agree? Okay. Now, let's consider the integral over the ellipse. Let's call the ellipse gamma. Gamma is going to be the boundary of the ellipse, and d is going to be the inside of the ellipse. Let's consider the integral over gamma, area of an ellipse d with a boundary of d called gamma. Okay? So gamma is the boundary, the integral over gamma of this specific field. Why this specific field, you'll see in a second. F dot dr. So according to the theorem, and clearly an ellipse is piecewise smooth, because it's just smooth, not even piecewise. It's simple and closed, right? It's positively oriented if we positively orient it, right? So if the inside is d, and we're going to orient it counterclockwise, then it's going to be positively oriented. It's planar, right? So it satisfies all the requirements of the theorem. Okay, so the theorem holds. So what we get, so let's write what it is, the integral over gamma of, let's write it. I want to go to the farthest board for a second, where I wrote you some reminders here. So if gamma is a smooth curve, parameterized by r of t, x of t, y of t, I'm only looking at planar curves now, then we discussed the integral of a scalar function, which was this thing, and I'm not going to go over it right now because that's not what I want to use, and the integral of a vector field, PQ, which was this thing. F dot dr was just an indication for taking the field and taking the dot product with r prime. Remember this? This was the definition of the integral of the second kind, the one relating to vector fields. Okay? And what is this? When you open the components, it's p of x of t, y of t times x prime. That's the first component of these two. Plus the second components, q times y prime. Okay? And we wrote this, in short, as p dx plus q dy. Remember this? This is a quick review, really in a nutshell, of everything we did in several clips ago. Okay? Everybody remember this? Okay. So I want to use this notation. Okay? It's a very useful notation, easy to remember. P dx plus q dy. I want to use this notation. So let's do that. The integral of f dot dr over this ellipse gamma is the integral over gamma of p minus y dx plus qx dy. Do you agree that in that notation, this is precisely what we get? Good? Okay. Now, by Green's theorem, so here I'm using Green's theorem, this equals the double integral over the domain D, for which gamma is the boundary, of what? Of qx minus py. That was Green's theorem, right? dq over dx minus dp over dy, right? So qx is 1, minus py minus 1 is plus 1. So what I get here is 2. Do you agree? dx, dy. Good?
Is it still closed?
Is what closed?
The integral.
Here?
Yeah.
Yeah, you can add the circle here. It's the same curve, right? Okay, so what I want to do now is, does everybody agree to this? This is just a very straightforward application of Green's theorem on this specific field, which I chose for the following reason. I'm going to take 1/2 of this. Well, if it's 1/2 of this, then it equals 1/2 of this, and then it equals 1/2 of this, right? That still remains true. But what is 1/2 of the integral of 2? That's the double integral of 1. And what's the double integral of 1? That's the area of the domain. Do you agree? So this equals the area of D. And that's the reason for choosing this specific field F. So at the end of the day, the area of the domain D, for which gamma is the boundary, equals 1/2 the integral of this specific field over gamma. Okay? And note that this thing is true for any D with boundary gamma, providing they satisfy Green's theorem. I'm not using here in any way yet that D is an ellipse and gamma is the boundary of the ellipse. Okay, I didn't use that yet. I'm going to do it in a second in order to, for this example, but this is true in general. Okay? So do you see here that in order to calculate an area, which is a double integral, I'm just going to calculate a certain line integral. Okay? Let's do that. So in our example, I need to calculate this integral over the ellipse. I need to find a parametrization for the ellipse, right? and then calculate all the details. F of x of t, y of t, times r prime of t, dt. Right? That's the dot r prime of t, dt. So let's do that. So here's the, back to our example, the area of the ellipse D equals the integral. Well, let's parameterize the ellipse. So an ellipse is given by x squared over a squared plus y squared over b squared equals 1, right? That's what an ellipse, that's the equation of an ellipse in analytic geometry, right? Do you agree? And a parametrization would be, I think we mentioned this several times, would be something of the form a cosine, or let's write x of t equals a cosine t, and y of t equals b sine of t, where t ranges between 2 pi and 0. We mentioned this, right? That this is a parametrization of an ellipse. Okay? So this is our side explanation for what comes here. So the area of the ellipse, by our preceding arguments, is 1/2 the integral over the ellipse of f dot dr, where f was the field minus yx. That was the field f. So let's write what that is. So it's 1/2, and now we need the integral from 0 to 2 pi. Those are the bounds, the upper and lower bound of the parameter in the parametrization of, come with me just one board back to recall the formula, because we don't remember it very well yet. So it's this formula. This is what I'm going to use, right? I'm going to take p at x of t, y of t times x prime, plus q at x of t, y of t times y prime. This is what I want to calculate, right? So back here, p is just minus y. Y is b sine of t. So p of x and y is just minus b sine of t. Do you agree that this is p? Times x prime. What is x prime? Minus a sine of t. Right? Minus a sine of t. So let's clarify all these things. So this is p, and this is x prime of t. Plus q. Q is x. X is a cosine t on the parametrization. A cosine t times y prime. Y prime is b cosine t. B cosine t. So this is q, and this is y prime of t. Good? Did everybody follow? And all of this dt. And then it becomes very, very easy to calculate because things cancel out. So the minuses here become a plus. So I get ab times sine squared plus ab times cosine squared, which is just ab times 1. So it's 1/2. ab comes out of the integral, and I'm left with the integral from 0 to 2 pi of 1 dt. The integral of 1 is t. Evaluated between 2 pi and 0, it's just 2 pi. Divided by 2, it's just pi. So I get pi times a times b. That's the area of an ellipse. I think you knew that, right? Okay, so if the ellipse happens to be a circle, in which case a and b are equal, and we usually call them r, right? So it becomes x squared over r squared plus y squared over r squared equals 1, or x squared plus y squared equals r squared. then the area of the ellipse, which is now a circle, is pi r, or pi r squared. You definitely knew that, right? Good, everybody? Okay. Questions on this example? Everybody good? Okay. So let's sum it up. Here we did it for a specific domain, okay? But this is true in general. In general, back to this board, the area of a domain, providing it's a good domain in the sense that it satisfies, along with its boundary, it satisfies Green's theorem, the area of the domain of a domain can be calculated not only as a double integral of the function 1, but as a line integral over the boundary of this specific, very simple, user-friendly field. Okay? So you can consider this as a formula for calculating areas of domains. Good? Okay. So this was an example of using Green's theorem to transform a double integral into a line integral and calculate the line integral. What I want to do in the next clip is use Green's theorem to transfer line integrals into double integrals, which are going to be easy to calculate. Okay? So it goes both ways. That's coming up next.